Well, hello again. In this example, you will see how to use a spreadsheet to carry out the basic matrix operations required in the stiffness approach. Specifically, we will be looking at this three-member truss that has pin supports at three of the joints, with only one of the joints being able to move. We've been given some information regarding these. We know the material has a modulus of elasticity of 10,000 KSI. Members 1 and 2 have this cross-sectional area, and member 3 has this cross-sectional area. To facilitate this, we will go ahead and label our degrees of freedom, making sure to label the unrestrained degrees of freedom first. So I'll label this as 1 and 2, and then I can just go around to the supported or restrained degrees of freedom and label those as well. It will also help for the calculations if we can write out the coordinates associated with each of these joints. And we are going to write these out in units of inches. So you'll notice here that's 120 inches in the x direction, 0 inches in the y direction. With this information in hand, we can begin to develop the element stiffness matrices. So what I'll do is plug in the coordinates. So this is the beginning coordinate for x, the ending coordinate for x, beginning coordinate for y, ending coordinate for y. The way we tell which coordinate is the start is we come back here and notice that we can identify where the origin is. So what that arrow indicates is that this would be the starting, that would be the ending. This would be the starting, that would be the ending. This would be the starting, that would be the ending. So let's look at this for element number 1. I've got those coordinates dropped in. I've also got properties of E and A already typed in. What I want to do is calculate what the length is, and that length, L1 here, is calculated by taking the square root of the sum of the squares, where these terms in here are nothing more than the differences that one experiences between these and these. We can also calculate the AE over L term. And here's the formula and the cells that are used in order to do that. And once we get that, we can begin to plug those in right here in that matrix, recognizing that this is the element stiffness matrix in the local coordinate system. Really, kind of the last thing we want to do on here is go ahead and compute the quantities for cosine and sine of phi. The cosine of phi can be calculated as taking the difference between the x coordinates, dividing it by the length, and the sine of phi can be calculated as taking the difference between the y coordinates, dividing it by the length. So that information can then be plugged into the transformation matrix, where this cosine term is dropped in here, 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 and here, whereas the sine term is dropped in here, and the negative sine term is dropped into there. Sine term is dropped in here, the negative sine term is dropped into there. Once we have the element stiffness matrix in the local coordinate system, we also have the transformation matrix. We are prepared to calculate the global element stiffness matrix. You may recall that in order to get that, you take the transformation matrix and take its transpose, multiply it by the local element stiffness matrix and the transformation matrix again. So just being clear here, this is that small k, and this is the t term. So looking down below, what we'll do is we'll first carry out this multiplication, and we see that right down here. Here's that t term, here is the little k term, and there is the multiplication that is carried out. Then you'll take that quantity and multiply it by the transpose of that t, which is right here. We then simply do that for members 2, just recognizing different coordinates, producing different lengths and different sines and cosines, and member 3. Those element stiffness matrices now in the global coordinates can be used to develop the global stiffness matrix. And if we were to come in here and partition that global stiffness matrix according to the unrestrained and restrained degrees of freedom, this is the way it would be. You will recall that we only have 2 degrees of freedom that are unrestrained, and all the rest of them are restrained. So the partitioning is labeled as such: KUU for the unrestrained degrees of freedom, KRR for the restrained degrees of freedom, and then KRU and KUR as the cross terms in the stiffness matrix. We know that for our matrix operations we are only going to need these particular portions of the stiffness matrix. So I'll show you how those are assembled. What we would do is take the element stiffness matrices, all 3 of them here, and we would simply identify the terms that have the same subscripts. So for example, if I wanted to find the K31 term in my global stiffness, what I would do is I would scan all of my element stiffness matrices for a K31 term. I've got a term there, but in element 2 and 3 I don't have that. Let's look at another one. So term 1, 2, this is the 8.9 term, so we would scan through this and find I've got K12 right here, I've got K12 right here, K12 right there. Add those up and drop them in to the structure stiffness matrix. Let's look at K11. So that comes up to be 42.9. I would take the K11 term there, plus the K11 term there, plus the K11 term there, and that would produce the 42.9. And you do that for all the terms in the stiffness matrices, remembering that we still have this partition that is coming in here differentiating between the KUU and the KRU. Next, we are going to need to assemble the force vector for the unrestrained degrees of freedom. So looking up here, we have 29.7 kips in degree of freedom 1, and we have no force in degree of freedom 2, and then all the remaining degrees of freedom are unknown reactions. So I get this, the F sub u, I've got that force in the degree of freedom 1, 0 in degree of freedom 2, and for the rest of them I acknowledge those are unknown for me right now. To solve then for delta u, the displacement of the unrestrained degrees of freedom, I would then take the inverse of the KUU matrix, multiply it by my force vector. These are the quantities that result for those displacements. So I would take this, and I would take the inverse of it, and then we would multiply it by that force vector, which is right here. And we recognize that that whole computation will give us this vector delta u. Next thing on the docket is to compute the reactions. We will use the joint displacements to be able to do that. We need the KRU matrix, and it is a simple multiplication. So we look here, here's that delta u, here's that delta u. Here's the KRU, here's the KRU, and that will result in this vector r sub r. Okay, we have the joint displacements, we have the reactions computed, and the last thing we need to find are the member end forces. And this is a 2-step process. First step is we need to find what the joint displacements are in the local coordinate system. We denote that with the lowercase u. We then take the displacements associated with that member, in this case member number 1, and that's degrees of freedom 3, 4, 1, and 2. We have those in the global coordinate system, and then we perform this transformation to get it into the local coordinate system. This we have right here is my global vector, and here is my transformation matrix, and I'm performing that multiplication. The next thing we will do is find the member end forces in the local coordinate system. Denote that with the uppercase Q, and that is found by taking the element stiffness matrix and multiplying it by the displacements of the degrees of freedom in the local coordinate system U. So the spreadsheet calculation is going to be done in this fashion, where we take this right there and we multiply it by that stiffness matrix, which is right here. And what that'll do is that will produce for us this particular vector. And then in order to get the correct sign on this, we know that the axial force is 17.408. This term right here is the one that gives us the correct sign. So that's how we knew that this is in tension. We perform that same operation for members 2 and 3. Then we can report the member forces as such. That concludes this example. As always, it is a beautiful day for studying structure.